Okay, first of all, let's start with what is a probability. Probability is a way of estimating the likelihood of something happening. It is defined as the chance that a certain outcome is going to take place, and its values extend from 0 to 1, where 0 means an event is impossible and 1 means an event is certain. Probability is used in understanding and predicting patterns under condition of uncertainty. Next, we move to project overview. This experiment serves to observe and analyze the spin time of a freely split coin standing on its edge. A recording of the time is made repeatedly to study variation in the result, hence establishing the experimental probability involving the outcomes in the time of spinning. This is also an experiment that would allow us to clearly contrast theoretical expectation with experimental outcomes about the way probability works in real life. Now, we move to methodology. So our goal is to measure the time t a coin spin before falling flat. Number of trials 20 times. Next, setup and tools. A coin, stopwatch, flat table surface, one experimenter. The number 3, we got procedure. First, place the coin upright the table and spin it. Second, start the stopwatch immediately when the coin begin to spin. Third, stop the stopwatch when the coin fall flat and record the time. Number 4, repeat for a total 20 trials under the same condition. Now, let's watch the video we doing the experiment. Let's answer the question. So the question number 1 is define one trial outcome. The trial outcome is the time t in second that the coin spins before stopping in one trial. As an example, the coin spins between 10 to 20 seconds. Question number 2, compute probability of t more than 3.5 and less than 4.5 and probability of t more than 4. For the first one, p t more than 3.5 and less than 4.5 is equal to 0 over 20, and we get the answer is 0. The next one is probability t more than 4 is 20 over 20, which is equal to 1.
Okay, so this is the result that we got from the experiment. Okay, so for the question 3, we want to find our mean and standard deviation. So for mean, the formula is total of spin time divided by total of trial. So total of time equal to 310.6 seconds and total of trial equal to 20. So the answer that we got is 15.53. So for the standard deviation, the formula is total of time minus mean and divided by total of trial. So 310.6 minus 15.53 and divided by 20, and the answer is 4582.44. So for the question 4, we want to find probability A less than equal mean and probability A greater than mean. 9 readings are below the mean and 11 above the experiment. Therefore, probability T less than equal 15.53 equal to 9 over 20, which is 0.45. And probability T greater than 15.53 equal to 11 over 20, which is 0.55.
Now we will move to discussions. The raw data show that most readings fall between 14 and 20 seconds, with few slightly lower or higher. This means that the hand movement causes some small random variation around an average of 15.53 seconds. We will move to question 5. Given t greater or equals to 3.5, find P of t greater or equals to 4 given t or greater or equals to 3.5. We'll put it into the formula, which is P of t greater or equals to 4 intersect t greater or equal to 3.5 over P of t greater or equals to 3.5, which we will get 20 over 20. Based on our data, we will get 1. So the answer is 1. Moving on to question 6. Which range produces the longest average spin? Based on our data, the most frequent values are between 18.1 second and 20.0 second, which represents stronger hand flick and consistency on spinning technique. Moving on to calculation of theoretical probability. Because the observed data evenly spread between 0 and 5 seconds, we will assume a uniform distribution where every value in that range is equally likely. So 1 over 5 minus O equals to 1 over 5, which we will get 0.20. Probability that spins between 3.5 seconds and 4 seconds is 0.20 times 4 minus 3.5, which we will get 0.1. The theoretical probability for spin time less than 3.5 is 0.20 times 3.5, which will equal to 0.07. Now, for the comparison, the theoretical probability of 0.1 is lower than the experimental result of 1. The difference may be due to limited sample size, hence spin technique or measurement rounding. With more trials, the experimental probability would likely to approach the theoretical value, showing how probability describes real-life random behavior.
Next, I will explain the question for chapter 3. So for the first question, we need to find k and fx. So we use the interval from 0 to 5, kx squared dx equal to 1. So first we integrate the x squared and then we will get x to the power of 3 over 3. Then we substitute the 5 into the expression, it will get k times 5 to the power of 3 over 3 equal to 1. And then we will get the final answer, which is k equal to 3 over 1 to 5. And then we find the fx. We use the interval from 0 to x, 3 over 125 t squared dt. And then first we integrate the t squared, it will get 3 over 125 times t to the power of 3 over 3. And then we substitute the x into the expression, we will get the final answer, which is x to the power of 3 over 125. So we get the fx equal to 0, it will be elsewhere, x to the power of 3, it will get 0 less than or equal to x or less than to equal to 5. And then the 1 will get x is greater than 5. Next, for the question 2, compute ex and variant x. So first we equate ex, use the formula x times fx. So we will get x times 3 over 125 x squared. So like usual, we integrate the x squared, it will get x cubed, we will get x to the power of 4 over 4. And then we substitute the 5 into the expression, we will get the final answer, which is 1875 over 500, which is 3.75. And then we need to find the variant x, but first we need to find the ex squared first. We use the formula interval, we use the interval from 0 to 5 x squared fx, we will get x squared times 3 over 135 x squared. And then we integrate the x to the power of 4, we will get x to the power of 5 over 5. Next, we substitute the 5 into the expression, it will get 1875 over 125. And then ex squared will get equal to 15. So after we get the ex squared, we can use the formula var x equal to ex squared minus ex to the power of 2.
So we substitute the ES squared and EX to the power of 2, which is 15 minus 3.75 to the power of 2. And then we press the calculator and then we get 0.9375. So that is the variance. So lastly, for the question 3, obtain origin of moment 1, origin of moment 2 and moment. So first raw moment, we use the formula origin, moment of origin equal to EX. So we can get interval from 0 to 5 x times 3 over 125 x squared. And then we can integrate the x cube, we will get x to the power of 4 over 4. So next we substitute the 5 into the expression, we will get 3 over 125 times 625 over 4. And then the final answer, we will get 3.75. Next, for the second raw moment, we use the formula of moment of origin equal to EX squared. So we can get the interval 0 to 5 x squared times 3 over 125 x squared. And then we integrate x to the power of 4, it will get x to the power of 5 over 5. So next we substitute the 5 into the expression, it will get 3 over 125 times 3125 over 5. And then the final answer we will get 15. So lastly, we need to find the moment generating function. So the formula is E times e to the power of tx. So we can use the integral from 0 to 5 e to the power of tx times kx squared. So e to the power of tx 3 over 125 times x squared. And then we need to integrate the expression. Use the integration by part. So for the first IBP, we let u equal to x squared, and then du will equal to 2x dx. And then the dv is equal to e to the power of tx dx. And then v we will get e to the power of tx over t. So we substitute to the formula of integration by part, which is uv minus integral u du, v du. So we will get x squared times e to the power of tx over t minus integral e to the power of tx over t times 2x dx. And then we integrate the right hand side, we will get x to the power of x e to the power of tx. And then after we get this, we need to use the second integration by part. So it will get u equal to x, du equal to dx. For the dv, it will equal to e to the power of tx dx, v equal to e tx over t. Then we substitute the formula, you will get x times e to the power of tx over t minus integral e to the power of tx over t dx. And then we integrate the e to the power of tx, we will get e to the power of tx over t. And then we times the 1 over t, it will get x e to the power of tx over t minus e to the power of tx over t squared. And then after that, we substitute back all the expression, it will get x squared e to the power of tx over t minus 2 over t times x e to the power of tx over t minus e to the power of tx over t squared. And then we substitute the integral, which is 5 and 0. It will get e to the power of 5t times 5 squared over t minus 2 times 5 over t squared minus 2 over t cubed. Minus, substitute the 0 into the expression, we will get e 0t times 0 squared over t minus 0x over t squared minus 2 over t cubed. And then the final answer, we will get moment generative function equal to 3 over 125 in bracket e to the power of 5t times 25 over t minus 10t squared minus 2 over t to the power of 3 minus 2 over t to the power of 3. That's the final answer.
Conclusion that we can make from this experiment is this experiment allowed us to understand the difference between the experimental distribution of spin times and the theoretical probability that a continuous random variable will fall within a specific interval. It is reasonable to state that analyzing the distribution of a random variable, whether discrete or continuous, as in this timing experiment, plays a crucial role in solving statistical problems and drawing meaningful conclusions from real-world data. So that's all from our group, and thank you for watching.